All right, so in this video, we're going to talk about higher order derivatives, okay? So we've kind of touched on it in other videos when we talked about the applications of derivative, but this is the idea that we can't just take one derivative, but we could take as many derivatives as we want of a function. So higher order means like the second, third, fourth, fifth, nth derivative is possible. So let y equal f of x be a differentiable function on the interval I, and the following are defined provided that the corresponding limits exist. Okay, remember a derivative is just a limit, right? Okay, so the second derivative is defined to be the derivative of the first derivative, right? So to get the second derivative, I just take the derivative of the original function 2 times. So I take the derivative once and I get the f prime, but then I take the derivative again and I get f prime prime of x, double prime. So it could be written as d dx, dy dx. It could be written as d2, dy dx2. So this is just telling you it's like ddx squared kind of thing going on. And this here, that's the notation y double prime is a second derivative. So these are all notations that you might run into, so you need to be familiar with them, okay? The third derivative is the derivative of the second derivative. So to get the third derivative, you take the derivative of the original function 3 times, or you take the derivative of the second derivative twice or 1 time, and then it kind of gets a little hairy, right? But essentially this prime here, you're going to use 1 for the first derivative, 2 for the second derivative, and 3 for the third derivative. But after the third derivative, we start saying, like, maybe if it's the fourth derivative, I put a little 4 in parentheses up there. So like f and then parentheses 4, that tells me it's the fourth derivative, okay? So after 3, we kind of drop this because it starts getting a little crazy. I don't really want to write all those little primes up there, so we just put the number, okay? So we have s of t, which is, recall from earlier video, I think 2.2 maybe. This is the position function. It tells us how far we are away, the distance traveled. Now, v of t, we talked about that. That's defined to be the derivative, the first derivative of the position function. So that's the velocity function right there. I'm going 92 miles per hour, all right? Now, a of t, I think we talked about this just a little bit, but a of t is the acceleration function, and the acceleration function is actually the derivative of the velocity function. So to get this second derivative here, we take the derivative of the first derivative, right? Just like this rule was saying here, to get the second derivative, I take the derivative of the first derivative. And to get the position function where we start at, I have to take 2 derivatives to get the acceleration, okay? Now, j of t, you've always wondered, all right, I got position, how far I am away. I have velocity, kind of like my speed. I've got the acceleration, the change in speed. So what's the change in acceleration, you might ask? Well, this is what's called the jerk, okay? The jerk, you can kind of think of it, so your change in your acceleration, that jerk that you get that kind of pulls you in the car whenever your acceleration is changing, that is what's known as the jerk. It's the derivative. It's the change with respect to time of the acceleration, okay? Which is the second derivative of the velocity function, and it's the third derivative of the position function, okay? So let's take a function, and we're going to do higher order derivatives. I'm going to find f prime. I'm going to find f double prime, triple prime, f to the 4th, and f to the 5th, okay? So let's do it. Well, what's the derivative of sine of x? That's one of our rules. Derivative of sine is cosine. Okay, so we got f prime. Now, how do we get f double prime? I have to take the derivative of f prime. What's the derivative of cosine? It's derivative of cosine is equal to negative sine. That's our rule. We got to remember those. If you remember those rules, then you can get these derivatives, okay? So if I look at this, to get the next derivative, to get the third derivative, I take the derivative of the second derivative. And so the derivative of negative sine, I can pull that negative out front. And so I'm just taking the derivative of sine, which I know is equal to cosine, okay? Now, the derivative, the fourth derivative is the derivative of the third derivative, okay? So the derivative of negative cosine, I can pull the negative out front. So the negative comes out front, and then I take the derivative of cosine. Derivative of cosine, I think, is negative sine. So that's equal to negative sine. So negative and negative make a positive sign, okay? So that's the fourth derivative. Now to get the fifth derivative, all I got to do is take the derivative of the fourth derivative. So I'm going to do that. So the derivative of the fourth derivative, so derivative of sine. Well, guess what, guys? You see this, how we've gone? We took four derivatives and we made a cycle back to sine x. Interesting. So the derivative, the fifth derivative of sine x is equal to cosine x, all right? So once you get 1, 2, 3, 4, guess what? The fifth one gets us right back to sine. So it's kind of like a cycle, okay? So derivatives of sines and cosines, if you take enough derivatives, you're going to get right back to the original function you started with, okay? Pretty interesting. Now, that's because of the periodic nature of the sine and the cosine, okay? And if you shift it, then it kind of overlaps on itself, okay? So kind of interesting. So now let's take a higher order derivative here. I want to find the derivative. I want to find the second derivative, and I want to find the third derivative, okay? So we've got our function here. And so if I take this, what I need to do here, this is good to use the power rule. This is good to use my e to the x rule. But this one here I need to put into rational form, the square root. It's understood that this is a 2 and that this is a 1 because there's one x inside, and the square root means you need 2 of this copy to get out of the house. And so I use my horsey and rider rule. So I get x to the 1 over 2. The rider goes on top, the horsey goes underneath. Now the derivative, how do I take the derivative of this? Well, the 2 comes out front, okay? So 2 times 2 is 4. And then when I subtract 1 from the exponent, I get 1. Okay, what about this one here? Well, 7 is just a constant, so I just got that. But the derivative of e to the x is so easy. It's e to the x. And then what about here? This one's the tricky one, right? So this one I have 1/2. I bring 1/2 out to the front. But then I do what? I do 1/2 minus 1. That's the rule, right? 2 minus 1 got me the 1 there. So 1/2 minus 1 gets me negative 1/2. Ooh, interesting. I need to simplify this here. So that's 4x plus 7e to the x. And then this negative exponent comes to the denominator. So that's 1 over 2 and then x to the 1/2. And then I can convert back to my radical form, square root of x in the denominator there, okay? But if we're going to take the next derivative, I take the derivative of this. So I want to stay in this form here when I'm taking derivatives because I can use the power rule. Can't use the power rule in this form. Got to convert to this form. So it's got to look like this to use your power rule, okay? So let's do that. So let's take the derivative. So if I take the derivative of this, I get the second derivative. So what's the derivative here? 1 comes out front. 1 times 4 is 4. and subtract 1 from 1, I get x to the 0. This one's the same thing again. E to the x is e to the x. Hey guys, y'all see something here? No matter how many derivatives we take of this, it's just staying the same. Interesting. Okay, what about this one though? 1/2 times -1/2, that's -1/4, right? Ooh, uh-oh. Have I made a mistake? No, okay. So I have the 1/2 and the 1/2 written there. I bring the 1/2 out front, and then what do? I take -1/2 and I subtract 1. That's -1 and 1/2, which is -3/2, I think. Okay, yeah. And so I can simplify this. X to the 0, remember that's just 1, so 1 times 4 is 4. This is still the same, 7e to the x. And then this one right here, multiply through, I get -1/4. And then this one here, x goes in the denominator to the 3/2. And so it's understood to be a 2 there whenever I do my radical form. Okay? Now we want to stay in this form here. We could clean that up a little bit to be -1/4. That's, might help us a little bit. To get our g triple prime, we take the derivative of this expression. So what's the derivative here? The derivative of 4 is 0, right? So I'm looking at this right here. The derivative of a constant is 0, all right? The derivative of 7e to the x, well, guess what? It's the same as it was here, 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 and now here again. Okay? Now this one here, I multiplied through, I got that. What do? I take my exponent, I bring it out front. Okay, so I have -3/2 out front, and then I subtract 1 from -3/2, and I get -5/2. Okay, so I can simplify this. I don't have to write the 0 anymore. I'm going to write the 7e to the x, and then a negative times a negative is a positive, and then I have what? 3 in the top and 8 in the denominator. So 3 over 8, and then this right here is 1 over x to the 5/2. Rider goes up top and the horsey goes underneath, so the rider's in the house and the horsey, that understood 2, is right there outside. Okay? All right, so these are my simplified answers over here. So that's G prime, G double prime, G triple prime. All right, guys, hopefully video was helpful in explaining the higher order derivatives. Essentially, we can just take as many derivatives as we want until we get tired, right? So, and when you get into Cal 2, we'll talk about the idea of taking infinite derivatives, okay? All right.